Is the slide visible to you?
Yes, ma'am.
Yes.
Okay. So today we begin with the next topic or next class of image processing operations, that is compression. We all know the need for compression. Compression is mainly required for the two reasons. We need to save the space for storage and we need to save the time for transmission. Right? We have a fixed rate of transmission generally depending upon the channel, and for that fixed rate of transmission I want my data to be reduced so that the transmission time is also reduced. So I want to reduce the transmission time, I want to reduce the storage space, that is your memory required to store the data. For that I need to talk about redundant data. Redundant data is something which is present in the data but is not necessarily important to be transmitted. Right? So if I have something, it may have two parts. One of the part of the information, one of the part of the data is my information. Right? Information is something which is very important to me, and this I need to.
Excuse me, ma'am.
Yes, child.
Ma'am, we can't see what you're writing right now.
Okay. Now is it visible?
Yes, ma'am.
So anything which we need to transfer, suppose this is the big block of data which needs to be transferred. This has two important things with itself. One is the information, that is the content which is having the information which is very important for us to be transmitted. Whereas there is some extra data, some redundant data which may be a copy of this information or which may be something other which is not much important, which does not convey as much information. We call this redundant data, right? So how to get the compression achieved? From this data, if I take this information part only and try to somehow suppress this redundant part, then I'll achieve compression so that the entire thing this big can be represented with only a small number of bits or small component, right? But this does not mean that I should cut the entire redundant thing, but my aim is to reduce this redundancy as much as possible, right? Redundancy is defined mathematically in terms of compression ratio, where compression ratio C is basically nothing but B upon B dash, where I mean that if the original number of bits were B dash and now after compression I have used only B number of bits. For example, if I had 100 bits initially, so B dash was 100, but I could use only 90 bits to be transmitted. In that case, my compression ratio is 0.9, right? So 90% of the information, 90% of the data has been used, right? Using this compression ratio, I can talk about the redundancy. How will be the redundancy calculated? 1 upon 1 minus this, right? Something wrong I did? Um, this is 10 by 9. Redundancy is coming out to be negative, which is not possible. This I took wrong. This should be inverse. So B corresponds to original size. Ah, now it makes sense. B dash is the compressed size. So I have it as 10 by 9. This is my compression ratio that has been achieved. Right? So I have here 9 by 10. This is 1 minus 9 by 10, which is nothing but 1 by 10. It means 1/10 of the data was redundant. So I could have reduced by 1 by 10. This much amount of information, this much amount of data was irrelevant. I could have reduced that so as to achieve a compression ratio of 10 by 9. Right? Now to implement compression, when we say we have to reduce this redundancy, we need to take care of three different types of redundancy. Right? The first kind of redundancy is coding redundancy. Coding redundancy refers to the redundancy or the unwanted number of bits in the code. It means I have four symbols, say I need to transmit 0, 1, 2 and 3, which could have been done using 2 bits of information per symbol, but I unnecessarily use 3 bits. So that 0 is given the code 0, 0, 0, 1 is given the code 0, 0, 1, 2 is 0, 1, 0 and 3 is 0, 1, 1. So unnecessarily I have added a third bit. So this bit becomes redundant. I can work without having this bit. So I can reduce the number of bits that are used in the coding way so as to code the symbols. I hope you remember the difference between source and symbol. A source is something which generates the symbol. Suppose I have 3 or 4 symbols that are generated, the things which are sent out. For example, the source gives out the vowels. So in that case, these S1, S2, S3, S4, these will be referred to as symbols. And for a source which gives out vowels, the symbols would be A, E, I, O and U. Right? So source is this complete thing. Symbol is the intermediate thing that it gives out. Combination of symbols will be referred to as word. This is word. Right? So your source may give out some words based upon some symbols. Right? So if the number of symbols is less, I should use smaller number of bits per symbol. Right? But the simplest case is I use equal number of bits per symbol. Okay? But later on we will see that we can have variable length coding so that the number of bits required is not equal for all the symbols, and we'll see how this works out for compression. The second type of redundancy is spatial or temporal redundancy. Spatial or temporal redundancy refers to the repeated information. This refers to repeated information in the image. Right? So we do not want to send the repeated information again and again. So we need to try and save some data so as to not send the repeated information. The third is irrelevant information. Irrelevant information simply refers to the information which is generally not taken care of by the human visual system. The examples are shown in the next slide. This is an image where I have 256 cross 256 image. Each pixel is represented with 8 bits, but now here I have only a fixed number of gray levels. I have only 4 gray levels. The gray level, say this is the first gray level, the second gray level, the third, and the fourth one is the gray level which represent this line. So though I have used 8 bits per pixel, but I have only 4 gray levels. So I should have worked with only 2 bits. So 2 bits was sufficient to transmit the information in this image, but still I am using 8 bit per pixel. So this is referred to as coding redundancy. So this is an example of coding redundancy. Unnecessary number of bits are used for the code for representing the symbol. Right. The second image here shows the horizontal lines running for the same gray level. Suppose this line, this has the gray level 10. So for all 256 pixels in this row, the value is 10. If this is the case, then I should not be required to send 10 256 times. Right? It is something which is repeated. I could have simply said that there are 256 pixels with value of 10. So I need to simply send two data. This, the value, and the number of pixels with the same value. Right? This is referred, this way of writing this, the conveying the information is referred to as run length coding. So this run length coding is much useful when we are having this repeated information in the image. This is referred to as spatial redundancy, the repeated things. And we call it temporal redundancy because over time the things get repeated. Over the pixels the thing is repeated. The third image here shows you the third type of information, the third type of redundancy, that is psychovisual redundancy. Where by looking at this image, it appears as if there is nothing that should be important to us, right? But actually there lies some information in the image, right? Therefore, now we do not need to send the entire thing. Instead, if we look at the histogram is concentrated over a small area, so we should be able to send this information only. Rest everything can be encoded in a single bit or the lesser number of bits. So again, the information which is not relevant to us, these symbols which are not used anywhere in the image, we can give them a different code, a smaller code, so that we save on the amount of data. Right. Coming back to the first kind of redundancy, that is your coding redundancy. Here, where I have excess number of bits used per symbol. This is the example. The four gray levels that are used in the image are shown here as 87, 128, 186 and 255, and for rest of everything, rest of the gray levels, I say the number of the value is 0. The probability is 0. This gives me the probability of occurrence of these gray levels. Since none of the other gray level exists, so the probability becomes 0. But still I have 256 gray levels, so I should be using 8 bits. So for transmitting these four values, I required these many bits, right? But if I use a variable length coding, a variable length coding is a method where the symbols with high probability are given smaller codes. So anything which has high probability, this gets a smaller code in length, like lesser number of bits. But the symbols which have low probability, we can assign more number of bits to them so that they are less used, they have low probability. So at a very small amount of time, for a very small cases of pixel, I will have longer codes. Otherwise, for high probability, for maximum cases, I will be having smaller codes which needs to be transmitted. So here the symbol with the highest probability is 0.47, that is ARC128. This is given the smallest code of a single bit. As the probability decreases, as I go to 0.25, the probability, the number of bits utilized is 2. As I move further, 0.25 or 0.03, the number of bits keep on increasing. So the total number of bits required per symbol is not the same. So we expect that this way we should be able to achieve some compression, right? How do we actually mathematically quantify that this is useful to us? We calculate the average bit length. Average bit length is simply given as summation of individual bit length for each symbol, the individual bit length multiplied by the probability of that symbol. So for example, R87, the number of bits for this variable length code is 2 and the probability of this symbol is 0.25. So I say 0.25 gets multiplied with the number of bits, which is 2, plus the second symbol has the probability 0.47, so I have a 0.47 here, multiplied by the number of bits required, which is 1, so multiplied with 1. And similarly 0.25 gets multiplied with 3 here, 0.03 gets multiplied with 3 here. So this gives me an average bit length of 1.81, whereas here the average bit length was 8 bits. So I achieved quite a lot of compression here. From 8 bits per value per symbol, I have reduced just to 1.81 bits. Right? So what is the compression that I have achieved? I initially had 8 number of bits. Now I have 1.81 bits per value. So the compression that has been achieved is 4.42, which simply means that there is a redundant data which is 77.4%. So this much amount of data can be removed or suppressed by using the variable length coding. Right? So that would be the first class of algorithms which will mainly target to reduce the coding redundancy. It is not always possible to have all the three kinds of redundancies reduced, but the main aim is that at least some of the redundancy should be reduced. Either of the three, at least we could have achieved either redundant. We could have removed the either of the three type of redundancy, at least one of the three type of redundancy. The second is the spatial or temporal redundancy. We already talked about it. This gives me the histogram, which simply says that every gray level has the equal number of pixels allotted to it, which is having the probability 1 upon 256. So I use a run length coding and I simply say that I have all the values which varies from 0 to 255. So I will use 8-bit representation for these values, right? And now rather than repeating this 8-bit value for 256 times, I simply say that this value 255 has a run of 256, right? So I again use 8 bits here, 8 bit for gray level, 8 bit for run. So I define it as an ordered pair every time, and I say that these 256 values are now coded in 16 bits only. Otherwise वैसे कितनी ज़रूरत होती? 258 bits per pixel and there are 256 pixels. So actual हमारा requirement क्या था? 256 times 8 bits. These many bits were required to represent one row. Now if I use this run length coding, RLE, how many bits do I require per line? 8 bits required to define the gray level and 8 bit required to define the run, which is 256, right? So I have another 8 bit. So in all how many bits? Only 16 bits. This is for one line. Here also for one line. So how much is the compression that I have achieved? I have achieved a compression of 256 into 8 upon 16. 128. So the compression achieved is 128. It means see how high is the redundancy. 127 upon 128. Right, almost 1. It means almost 100% of the data that we could have used here is redundant. It is very small amount of data which bears the information, which उस information के साथ हम पूरा image reconstruct कर सकते हैं. So this is your second class of algorithm which we will be using to reduce the spatial redundancy. Right? We have already talked about. Now some mathematics. How to measure the image information? Image information is measured in terms of logarithm, log to the base 2, where I have the information defined as minus of log PE. This is the probability of having the event E or the symbol E. This you know, you have studied in maths, you have studied in digital communication, you have studied in ITC. The amount of information conveyed by is given by this expression. Now the important thing is entropy. Entropy is referred to as the average information per symbol. Per source output means per symbol. So if this is my source which gives out symbols A1 to AJ, each with the probability PA1, PA2 till PAJ, the entropy is defined as probability into log of its own, log probability. This is all to the base 2, right? So we have a symbol, let's say A1, then whatever is the probability PA1 multiplied by log of PA1. Since we define this in the terms of information here, so we have the negative sign because information itself has a negative sign. Why do we have this negative sign? Because this gives me probability. Probability is always less than 1. So it will always be a negative sign, so your information will always return a positive value, right? The same thing happens here. The entropy is given by this formulation which says minus of summation for each symbol, the probability of the symbol multiplied by log to the base 2 of its own probability, right? These symbols, the A1 till AJ, they are independent of each other. It has no relation कि एक बार अगर A1 आ गया है, then the probability of having A2 is higher or not. There is no such relationship. All the symbols are statistically independent. If this is the case, we say that the source is zero memory source. It does not require any, it does not use any memory, so it does not have any dependency of one symbol over the other. All the symbols are independent. So in general, for our case, we will always consider this zero memory source, so that we consider all the symbols are independent of each other, right? This is how your entropy has been calculated for the same image with the 4 gray levels. This is the probability for each gray level given. So we simply put into the formula minus of probability R87 log to the base 2 probability of R87 plus probability of R128 into log to the base 2 probability of R128, and similarly for the other two cases. So what is the average information conveyed per symbol? It is 1.6614. Right? But whenever we are using the compression, we say that we have this much data, we remove certain portion of data or we reduce this data, and we are using this much part of the data only, which gives us most information. But it has to be mathematically defined कि हमें कितना part use करना is okay with me. So for that we use fidelity criteria. Fidelity criteria, as the name suggests, this is the criteria which should be met such that the compressed data is able to represent the uncompressed data. ऐसा नहीं होना चाहिए कि data is completely turned out, it is completely changed. The two should be very close to each other. So the two should be very similar. So अगर मेरे पास काफ़ी ज़्यादा information नहीं है, like in the special case, but still I want to have some extra redundant data, so I may use this redundant data to provide me with the more information. So that this is not sufficient, इससे मेरा data बहुत corrupt हो रहा है, so I use some part of this redundant information to be used so that the reconstructed data from the compressed data is very much resembling the original data. So how do we measure this fidelity criteria mathematically? We generally use root mean square error or the peak signal to noise ratio. We already discussed these errors while we talked about the criteria for comparison for enhancement and restoration. The root mean square error, you simply take the difference which is treated as the error, the difference between the original data and the decompressed data, the data which is reconstructed after the compression has been done. So the difference between them is treated as the error. You square the error, summate the error divided by the total number, that is you take the average here and then you take the root. So you have the root mean square. We want this error to be as small as possible. The other fidelity criteria is signal to noise ratio, and the similar criteria is peak signal to noise ratio. Again, with the difference, signal to noise ratio means whatever is the decompressed pixel, each value of that pixel is considered. Whereas if I use PSNR as my measure, then this F cap will always be represented with the maximum value. Right, that is the only difference. Rest it remains the same. This is the strength of the signal. This is the error which is taken the mean for. So this is signal to noise ratio. PSNR will replace this as F cap with maximum value. The three images here again, slight compression has been done. The number of bits here are reduced somehow, here further reduced, but this results into some distortion in the line, some distortion along the line. Here, due to that compression, some part of the lines are lost. The three images are very much different from each other. Here we say that the root mean square error is 5.17, which is quite small as compared to the total size of the image, which is 256 cross 256 multiplied by 8 bits. Right? Here the root mean square error slightly increases, so we expect that the quality of the image has been degraded. Fine. But again, in the third case, the root mean square error as compared to the first one is 14.17, which is less than this 15.67. This simply means that this image, the third image, should be a closer match to the first image, because the root mean square error is less as compared to the second one. But this is actually not the case. So root mean square error is generally okay for mathematical ways, but this does not exactly convey that the amount of information or the amount of distortion seen in the image is always less. Right? Therefore, we use multiple fidelity criteria generally to define the quality of the compression that has been achieved. राइट अभी अगर हम खाली रूट मीन स्क्वायर एरर देखें तो इसका रूट मीन स्क्वायर एरर इज लेस एज कंपेयर टू दिस रूट मीन स्क्वायर एरर, but here the information is completely lost. Here the information is distorted in second image. That is okay with us, right? But here the information is completely lost. We do not know how these lines are connected over this region. So having a smaller root mean square error does not always mean that your compression is better, right? Here unnecessary things have been seen, but still the root mean square error is less. So now we look into the different methods which are required to achieve or reduce at least one of these kind of redundancies. So the general way of representing a compression and decompression system is something like this, which says I should have a mapper. Mapper simply means that I should have some encoding done, right? Encoding done means for every symbol I should have some code assigned. This is the basic thing that we need to work with, right? Then we may have a quantizer. This is an optional thing. You have studied a quantizer. A quantizer is something which divides the entire range into certain number of intervals and then use one defined level to represent any value lying in that particular interval, right? This quantizer is generally causing the loss of information. So whenever a quantizer is used, we say that the compression method is lossy, because within this range I know the value being given out is this, but once I receive this value I do not know what is the exact value, so I will not be able to reconstruct the original image. So whenever I use a quantizer, I will result always into some lossy compression, right? Once the coding has been done, then the code is sent to the channel. At the receiver end, we need to decode it, right? And then inverse mapper means जो भी हमारा code आया, what was the symbol that was assigned to it, and based on that we will reconstruct the symbol. The first class of algorithm that we are going to see is variable length coding. The first variable coding is the Huffman code. When I say variable length coding, these variable length coding works on the basis of probability of occurrence of a symbol. Higher probability means smaller code length, means less number of bits. Lower the probability, longer is the code length. Okay. Let's work with an example to understand this better. Let us say I have 4 symbols, let's say more than 4, E and F. So each of this symbol has some probability of occurrence, right? Say A is 0.4, E is 0.2, B 0.15, 4, 5, 6, 75, 80, 84 and 100. Is it 100 completely? 8, 9, 10, yes.
Yes, ma'am.
Now the sum of all the probability is 1. So now I have these probabilities defined, which simply says that A is having the highest probability of 0.4, E has the highest probability of 0.2. In all, I have how many symbols? I have 6 symbols. So if I use equal number of bits per symbol, I need at least 3 bits per symbol, so that I have 000 as A, 001 as B, 010, 011, 100 and 101 for each symbol. So what is the average length? 3 bits. But when I use this variable length coding, that is your Huffman code, the first step would be that I arrange these symbols on the basis of reducing probability. The probability should decrease. So the highest probability is 0.4. So I should have the symbol A placed first, followed by the next probability of 0.2, which is E. Then I have 0.16, which is F, 0.15 B, 0.05 C, and finally 0.04 D. Why do we arrange this in this order? So that when I move in this direction, I increase the length of the symbol. Right? The length keeps on increasing as I move down, because I already said higher probability needs to have smaller code length, lower probability needs to have longer code length. For this Huffman code, if I have n number of symbols, I will always require n minus 2 steps. This is something which generally creates a problem to us, because अभी हमारे पास अगर 6 symbols हैं, so I'll need 4 steps of working. But if I have in real time, I have say all 26 symbols of the alphabet, then I'll need 24 steps to code them. Right? अगर मैं colors की बात करूँ, I have 256 colors, 256 gray shades, so I need 254 gray levels, 254 steps, so as to encode them. So greater the number of symbol, longer will be the time required for coding. That is one of the limitations for Huffman code. Let's see how this code works. For using this Huffman code, what we keep on doing is we keep on clubbing two values from the lower end and add them together. The summation will again be arranged in the order of probability in the second step. Or I say this is my step 1. So I add the last two probabilities, the lowest probability, which will give me 0.09. So I have the new set of probability as 0.4, 0.2, 0.16, 0.15 and 0.09. So I need to rearrange them in descending order. So I preserve this all and this summation is placed here. Now again I add the last two probabilities and this will give me 0.24, right? So 0.24 will always be placed above this is greater than 0.2. So I should shift it upwards. So in step 2 the arrangement will change as 0.4. Then the summation of 0.24 will be placed here, which I got due to the sum of these. This 0.2 gets shifted downwards and 0.16. Step 3, I add the last two, which gives me 0.36. So the new arrangement would be 0.4, 0.36 and 0.24. I get it here. And lastly what I get is how much is this 0.6. So in step 4 I'll get 0.6 followed by 0.4, where 0.6 is achieved using summation of these two. So I completed the number of steps as 4, right? I had 6 symbols, so I completed 4 steps. Now I start assigning my code. So for that what I do is at every step I have to add one bit, right? The number of possible values for the bit is 2, that is 0 and 1. So in step 4 I represent the first highest probability as 0 and the lower probability as 1. This 0 is the code which is assigned to 0.6, which came from the sum of these last two probabilities. So I propagate this 0 backwards so that I get a 0 for 0.36 and a 0 for 0.24. But at this level I add another bit to distinguish between them, otherwise दोनों का code 0 हो जाएगा. So to distinguish between them I add another bit. So I put the code as 00 on the top and the code as 01 at the bottom. This 0.4 got the code 1, which needs to be transmitted backward here. So the probability for the code for 0.4 probability would be 1, right? Now the codes I have in this level 3 is 0.4 के लिए 1, 0.36 के लिए 00, 0.24 के लिए 01. But this 0.36 was made up of these two probabilities, so I backtrace this 00 to this. So in दोनों का initial code तो 00 हो गया, but now to distinguish between them I add the third bit and I give them the code 000 and 001. Whereas this 0.2, the 0.24 was given the code 01. So 0.24 came from here, so I backtrace it. So 0.24 का code कितना है 01, 0.4 का code कितना है 1. So I have the new codes for step 2. Come back to step 1 with back propagation, where the code for 0.24 needs to be propagated backward to these two. So what do? I propagate the code 01 backward and add the third bit. So 0 on the top, 1 at the bottom. The code for 0.16 was 001. So I trace it backward and the code for this would be 001. 0.2 का code था 000, so I keep it as 000. 0.4 के लिए code था 1, so I keep it as 1. Right? Backtrace again. The code for 0.4 is 1, 0.2 के लिए 30, 16 के लिए 001, this is 0, 1, 0, and I propagate this backward. 0.09 is the sum of these two probabilities. So the initial code is 0, 1, 1 for both, and I distinguish between them by adding another bit. So what is my final code book I get? A, E, F, B, C, D. The code for A is single bit 1, E is 3 bit, F is 3 bit, B is 0, 1, 0, this is 4 bit, and this is also 4 bit, right? So it though appears that I have to have 3 bits here, but I am having 4 bits here, so the compression must not have been achieved. But if we calculate the average length, how do we calculate the average length? Average length is for each symbol, what is the number of bits per symbol multiplied by probability of RK. The number of bits per symbol, or I say the length for each symbol RK multiplied by probability of RK. So what is the length here? That is 1 multiplied by the probability, which is 0.4, plus the length is 3 multiplied by 0.2, so 0.6, plus again the length is 3 multiplied by 0.16, so 0.48, 15 into 3, 0.45. Now 0.05, that is only 0.2, plus 4 into 0.04, that is 0.16. Add them, what do you get? How much do you get? 2.29, I guess. Is it correct? 2.29. Three, 9, 5, 111. Right, something 2 point something. So even though I am using 4 bits for 2 of the symbols, but still the average length is much less than 3 bit. This is only 2 point something bits per symbol. So the compression has been achieved, right? Now quickly looking at the decompression way. Suppose I have the data received as this, and this is my code table which is used for Huffman coding, right? Now how do I decode? I start reading the first bit and I try to look out in my code table if I have that code. So the first bit is 1. I have a code for 1. This simply means that the first symbol that was transmitted is A. I come to the next bit now. I have the symbol in my code table as 1. It means the second symbol transmitted is also A. But when I come to the third bit, I have started with the 0. I have so many options for symbol starting with 0, but single 0 does not exist. So I combine 0 with next bit. So I look out for 0, 1. If I look out for 0, 1, I again have 3 possibilities if I combine the further number of bits. So I just do not stop here, but I combine the third bit and look out for the code 0, 1, 1. 0, 1, 1 again gives me 2 possibilities if I combine the fourth bit. So I combine the fourth bit also. So now the code becomes 0, 1, 1, 1. So 0, 1, 1, 1 is the code defined for D. So D was transmitted. Again, the symbol has been covered till here. So I start with 0. I do not have any single 0. So I look out for 0, 1. I do not have any code 0, 1. I look out for 0, 1, 1 where I do not have any code. and then I look out for 0, 1, 1, 1, which again gives me D. The next is 0. 0 does not exist as a code, so I combined with the second 0, 1. 0, 1 is not existing as the code, so I look out for the third bit connected, that is 0, 1, 0. 0, 1, 0 exists as the code for B, so I stop at the combination of 3 bits and I say that a B is transmitted, right? Then I have to begin with 0. 0 does not exist as a code, so I look out for 0, 1. 0, 1 does not exist as the code. Then I look out for 0, 1, 1, which does not exist, so I look out for 0, 1, which means I need to have transmitted D. So what is the decoded data? This is AADDBD. How to check if this is correct? If I need to send out this using this code, what will I send? For A, I should send 1. Another A, I should send 1. For D, what is the code? 0 1 1 1. So I should have sent 0 1 1 1. Another D, 0 1 1 1. B means 0 1 1, sorry, 0 1 0. And finally with D, 0 1 1 1. The two are same. It means if I have this code table with me, then I'll be able to decode clearly. But the problem with Huffman coding is that if I do not, if I have two equal probabilities, then this creates a problem. We will see that special case tomorrow and we'll move on with Shannon-Fano coding. Any problem in today's class?